In this video, I'm going to show you how to compute the steady state, or the multiple steady states, of a positive feedback loop such as this one. So, in Tellurium, I already have a model with two steps that represents this positive feedback loop. For the first step, S1 and S2, the rate law is defined as V1 max times S1, so the forward direction, times V2 times S2 raised to this factor, which defines the positive feedback. The second one is the reverse direction, which is just a new rate constant times the concentration of S2. I have some initial conditions defined here, so let's just go r.simulate 0, 100, 1000 points, and then r.plot, just so we can see what this looks like. And here's the concentrations of S1 and S2 over time. So now I'm going to show you how to write a script that computes the multiple steady states of this model, using a simple method of looping through different simulations and observing what steady state each simulation reaches. First, I'm going to go m equals r dot simulate 0 to 10 with 100 points. Then I'm going to go r dot conserved moiety analysis equals true. And that allows us to solve those differential equations before accurately, only using one of them. Then I'm going to go print r dot steady state. Then I'm going to go print s r dot s1, comma r dot s2. I don't want that in the parentheses. Okay. Then I go for, this is our loop, for I in range. We're going to go through 20 times. R dot s1 equals random dot random, not phantom. And we've already imported the random, so we don't need to do that, but we would need to import random in order for this to work. Random star 3, then r dot s2 equals 3 minus r dot s1. This statement sets s1 equal to a random number between 0 and 3, and this statement sets s2 equal to the difference between 3 and the random number of s1. Then r dot simulate 0 to 10 with 100 points again. Then r dot then we print Okay, so we're printing each of the two species concentrations and then the sum of them just to make sure it stays at 3 the entire time. Okay, now when we run this, we can see that we end up with this funky table of numbers. The first thing to observe is that every single time we run it, we can see that S1 and S2 add up to 3 perfectly. That is good. Second of all, we will go and look at all these species concentrations of S1 and S2. We can see that there's going to be different steady states because they reoccur. The first one is going to have this 1.39 and this 1.60. The second one is going to have this 2.54 and this 0.45. Then we have the 1.39, the 1.39, the 1.39, the 2.54, then the 1.39 a whole bunch more times, the 2.54. Then we have this other one, the 2.180 and the 0.891. That's the third steady state. So we have observed 3 different steady states by starting this system at random points and running it 20 different times. Now, let's just plot one of these steady states. So let's pick this one. We're going to say r dot s1 equals r dot s2 equals and then r dot plot. We want to make sure this is out of the loop because that would be bad. First, we need r dot simulate. Zero comma 400 comma 600 r dot plot. Now when we run this, we can see that we start at this steady state. However, we end up at the 1.39 and 1.60. So just to try it, let's start at one of the other steady states. Let's start at the 2.541. Now when I run this again, we can see that it stays at the steady state the entire time. One last try, let's try it with the last steady state. Okay, run it one last time, and it stays there too. So this has shown us that the 1.39 and the 2.54 steady states are both the two stable steady states, while the 2.108 and the 0.89 steady state is unstable. And over time, with the minor fluctuations, we'll eventually reach one of the other two steady states because those are stable. Thank you for watching, and now you know a method for calculating the various steady states of a cyclic system in which moiety is conserved.